is electrical and physical design of logic gates. Electrical and physical design of logic gates. You will see that these things are covered in module 1 and module 2. So here in this we have some examples. Okay, first example is inverter. So in the inverter we have this schematic diagram. This is called as schematic diagram or schematic circuit. This schematic diagram is not to you all. How we draw this schematic diagram? What all the electrical connections we are following? So electrical connections under this is a MOSFET, P MOSFET, N MOSFET. Okay, and from here to here we have an electrical connection or wire. Similarly, at the top also we have a connection for VDD, and here ground side we have connection for ground. So here we use metal one, or wire for doing the connection. Okay, so drain to drain short and gate to gate short. These things we have seen in module 1. So electrically connect, how they are connected. Okay, that is there. And next what we have is different forms of inverter layout. Which one we have seen? Which one we have drawn in regular class? First one or second one? First one or second one? Second one we have drawn in regular class. This is the poly. Okay, poly is extended and we are writing input. This is source. This is P diffusion. Okay, this is N diffusion. P diffusion, N diffusion, this is poly. So whenever poly crosses the diffusion, it forms a MOSFET or transistor. Okay. So this is P MOSFET, this is N MOSFET. Correct? Source is connected to VDD, drain is connected to drain, source of NMOS is connected to ground. This regular layout you have seen it in the class, but this is also another form of layout of the same inverter. Here particularly we have not taken common poly like this, straight line formula. The vertical part is P diffusion, and here the vertical part from here to here is N diffusion, and poly I am crossing it horizontally. So this is forming a P MOSFET. Okay, now here I am shorting the poly with this poly. So the N MOSFET, P MOSFET, gates are shorted and that is the input. If you assume this as source, it is shorted directly to VDD. This as source of NMOS is shorted to ground. Both the drains are shorted and taken as the output. So both the layouts are correct. Okay, this is physical design. And the thing which we see using wires, that is electrical design. These are also the layouts of inverter. hard and fast rule that layout should be drawn like this only. Hinge draw ಮಾಡಬೇಕು ಏನು ರೂಲ್ ಇಲ್ಲ. Okay, so some depends on the designers. Some designers they prefer very compact area. ಹಂಗ ಕಾಂಪ್ಯಾಕ್ಟ್ ಏರಿಯಾ ಟ್ರೈ ಮಾಡಿದ್ರೆ there will be a risk of violating the rules, design rules. Again, they require lot of time and lot of effort in doing the layout. Some people they don't focus on more on compact area. They just want to do it and they do it. So either the example you can visualize in the lab. ಯಾರಿಗಾದರೂ analog part start ಆಗಿದೆ when analog part is start ಅಲ್ಲ you people will draw the layout in the lab. At that time you will see that your friend is using less area than you. ಅಲ್ಲಿ ಆ ಕಾನ್ಸೆಪ್ಟ್ ಬರ್ತದೆ and layout can be drawn anyway. Okay, this is also correct. Fine. All the three, they are also the layout of same inverter. Okay. In the same way, we have gates also. These are parallel inverter layouts. Parallel inverter layout करते हैं. Parallel inverter layout करते हैं. Inverters are connected in parallel. That layout that way. Yes, inverters are all how many inverters are there? Yes, this is one P diffusion. This is one P diffusion. This is one P diffusion. This is poly. This is N diffusion, N diffusion, N diffusion. Total how many transistors? Total how many transistors? 6. Out of 6, 3 are PMOS and 3 are NMOS. But the input is common. You are seeing only one input. Therefore, it is said that they are parallel inverters. So, each you are drawing 3 inverters, but they are parallel. This is also parallel inverter, drawn in some different way. Parallel inverter. You have taken only one diffusion. You have taken only one diffusion. MOSFET, MOSFET. And then they are connecting in parallel. In the same way, in the inverter. Here they are taking one N diffusion and they are creating MOSFETs and doing the connection. I think you would have inverters which are connected parallelly. Two inverters. See how to find out how many inverters are there. Yelling in the poly P division cross that is inverter. Sorry, that is the MOSFET. Poly diffusion layer cross that is the MOSFET. Okay. And these are the connections. Connection overlap MOSFET only poly and diffusion. When they cross, it forms a MOSFET. have NAND and NOR gates. I am going a little fast here. ಯಾಕಂದ್ರೆ ಇದು ಕಲ್ತಿದ್ದೀವಿ. ಇದರೊಳಗೆ ಯಾವ ಕಲ್ತಿವಿ ನಾವು ಕ್ಲಾಸ್ ಒಳಗೆ? First one or second one? Second one we have studied in class. So, ಇದನ್ನು ಕಲ್ತಿವಿ. Two polys we have taken. Although this is P diffusion, N diffusion. So VDD shorted to source of both the MOSFETs. Both the drains are shorted and drain is taken as output. So that output is going down connected to drain of NMOS. This is source and drain, they are shorted by default. Okay, and this drain again, if this is drain, this is source. Source is shorted to ground. And these two are the inputs. Now A of the B is extend ಮಾಡಿ left side A and B. This we have seen in regular class. This is one more way of doing the layout of NAND gate. Usually we have taken two diffusions separately. There are common diffusion into ಎರಡು polygon is here. We are taking two diffusions into different polys here, and these are the inputs. Okay. So in by default source type, these two are source which are connected to VDD. These two are drains which are shorted, and from there output is taken. You have to compare it. From this drain, okay, this is the drain now. The drain is the source. Each source are the next drain are the source. Okay. So it is drain, source. They are connected in series. NMOS are connected in series, but PMOS are connected in parallel. And this is one NMOS, this is one NMOS. ಹಿಂಗೆ ಮಾಡಬೇಕಂತಿಲ್ಲ. As I said, you have leniency. This is NOR gate. Now you have continuity. Which one we have studied? Again, second one we have studied. What first one? What is the difference? This connection is from source to ground. Okay, and this is the drain. So they are in series. PMOS are in series, NOR gate. So it is source drain is coming down. This is the output, and that drain is connected to the drain of two MOSFETs. And both the sources of MOSFETs are going down. This is parallel connection. This parallel connection they have just interchanged. So here source ke ground kotirilla, and these two become source and it is grounded, and these two become drain which are shorted. In line sensor there is shorting, and this is connected to output. This one will bandadalla, alli this one will bandadalla. Then they are shorting these 2 points, and from source they are giving the ground. ಏನಾದರೂ ಕನ್ಫ್ಯೂಷನ್ಸ್ ಡೌಟ್ಸ್ ಇದ್ದರೆ ಕೇಳ್ರಿ. ಸಿ ನೆಕ್ಸ್ಟ್ actually we are seeing the series connection and parallel connection of MOSFETs. Although series connection is parallel connection is but if you want to study in detail series connection is that what will be the time consumption for the signal to reach from VDD to output or output to ground. ಅಥವಾ parallel connection ಇದ್ದಾಗ time required ಏನಾಗ್ತದೆ. Okay, that analysis they are showing here. So here they are showing the series and parallel connection of MOSFETs. This side. So these two transistors are connected in series. These two transistors are connected in parallel. Okay. So what will be their effective resistance? ಏನಾಗ್ತದೆ? When they are connected in series, what will be their resistance? Double. R plus R. ಹೌದಾ? ಇಲ್ಲಿ ಏನಾಗ್ತದೆ? R by 2. Network analysis R1 ಮತ್ತೆ R2 ಆಗಿದ್ದಿಲ್ಲ. ಇಲ್ಲಿ ಏನಾಗ್ತದೆ? ಈಕ್ವಲೆಂಟ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಏನಾಗ್ತದೆ? R1 plus R2 ಇಲ್ಲಿ ಏನಾಗ್ತದೆ? R1 into R2 by R1 plus R2. ಹೌದು? So L resistance ಕಡಿಮೆ ಆಯ್ತು. Where resistance is decreasing and where it is increasing? Parallel ಒಳಗ decreases. Series ಒಳಗ increases. So we have an equation T is equal to R into C. What is T? Tau or time, tau or T. What it is? Tau or time. Time ಹೇಳತ್ತೀನಿ ನಾನು. Answer ಹೇಳತ್ತೀನಿ. Tau or T. It is time. Then T is equal to R into C. What is R? What is C? So now, if resistance ಇಲ್ಲಿ double ಆಯ್ತಲ್ಲ, ಇಲ್ಲಿ resistance double ಆಯ್ತಲ್ಲ, so what about it? T here. T ನು ಜಾಸ್ತಿ ಆಗ್ತದೆ, ಇಲ್ಲಿ resistance ಕಡಿಮೆ ಆಯ್ತು. So what about T? ಕಡಿಮೆ ಆಗ್ತದೆ. ಹೌದು? That analysis they are showing here. TR is the worst case rise time for NAND gate. Worst case ಅಂದ್ರೆ ಏನು? Worst case ಅಂದ್ರೆ the NAND gate. How many input combinations are there? For NAND gate, how many input combinations are there? We are taking two input NAND gates. Just input combinations are 0 0 0 1 1 0 1. ನಾಲ್ಕು input combinations. 0 0 ಇದ್ದಾಗ ಒಂದು ಡಿಲೇ ಇರ್ತದೆ. 0 0 ಕೊಟ್ಟರೆ ಒಂದು ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಆನ್ ಆಯಿತು, ಒಂದು ಆಫ್ ಆಯಿತು, ಹೌದು, ಔಟ್ಪುಟ್ ಬರ್ತದೆ ನಿಮಗೆ. ಸೊ ನೀವು 0 0 ಕೊಟ್ಟಾದ್ಮೇಲೆ ಟೈಮರ್ ಹಚ್ಚಿದ್ರೆ ಜಸ್ಟ್ ನ್ಯಾನೋ ಸೆಕೆಂಡ್ಸ್ ಅಥವಾ ಎಷ್ಟು ಮೈಕ್ರೋ ಸೆಕೆಂಡ್ಸಿಗೆ ಔಟ್ಪುಟ್ ಬಂತು, ದ್ಯಾಟ್ ಈಸ್ ದಿ ಡಿಲೇ. ಹೌದಾ? ನೆಕ್ಸ್ಟ್ ಯು ಚೇಂಜ್ ದಿ ಇನ್ಪುಟ್ 0 1 ಮಾಡಿರಿ. 0 1 ಮಾಡಿದಾಗ ಮತ್ತೆ ಯಾವುದೋ ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಆಫ್ ಇದ್ದಿದ್ದು ಆನ್ ಆಗ್ತದೆ, ಆನ್ ಇದ್ದಿದ್ದು ಆಫ್ ಆಗ್ತದೆ. ಸೊ 0 1 ಇನ್ಪುಟ್ ಕೊಟ್ಟ ತಕ್ಷಣ ಸ್ಟಾರ್ಟ್ ದಿ ಟೈಮರ್ ಆ್ಯಂಡ್ ಔಟ್ಪುಟ್ ಬಂದ ತಕ್ಷಣ ಸ್ಟಾಪ್ ದಿ ಟೈಮರ್. ಸೊ ದ್ಯಾಟ್ ಡಿಲೇ ವಿಲ್ ಬಿ ಡಿಫ್ರೆಂಟ್ ಕಂಪೇರ್ಡ್ ಟು ದಿ ಫಸ್ಟ್ ಡಿಲೇ. ದೆನ್ ಅಗೇನ್ ಚೇಂಜ್ ದಿ ಇನ್ಪುಟ್ 1 1 ಮಾಡಿರಿ. 1 1 ಮಾಡಿದಾಗ ಮತ್ತೆ ಸ್ವಲ್ಪ ಚೇಂಜ್ ಆಗ್ತದೆ. ಒಂದು ಟ್ರಾನ್ಸಿಸ್ಟರ್ ವಿಲ್ ಬಿ ಆಫ್ ಇದ್ದಿದ್ದು ಆನ್ ಆಗ್ತದೆ ಅಥವಾ ಆನ್ ಇದ್ದಿದ್ದು ಆಫ್ ಆಗ್ತದೆ. ಹೌದಾ? ಹಾಗಾಗಿ ಅಗೇನ್ ಔಟ್ಪುಟ್ ವಿಲ್ ಕಮ್. ಸೊ ಫಾರ್ ಎವ್ರಿ ಕಾಂಬಿನೇಷನ್ ಡಿಲೇ ಈಸ್ ಡಿಫ್ರೆಂಟ್. ಫಾರ್ ಎವ್ರಿ ಇನ್ಪುಟ್ ಕಾಂಬಿನೇಷನ್ ದ ಡಿಲೇ ಈಸ್ ಡಿಫ್ರೆಂಟ್. ಓಕೆ. ಸೊ ವರ್ಸ್ಟ್ ಕೇಸ್ ಡಿಲೇ ಅಂದರೆ ಏನು? ವರ್ಸ್ಟ್ ಕೇಸ್ ಡಿಲೇ the delay which is worst or taking maximum time, that is the worst case delay. Okay, so here I am taking TR as the worst case delay. Okay, whatever I have said, ಈಗ ಏನು ಇಲ್ಲ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡಿದ್ನಲ್ಲ ನಿಮ್ಗೆ series parallel resistance doubling and half, the same thing they are telling you mathematically. Okay. So they are writing the equation D is equal to R into C. What is C? C is M into CD plus CL. What is CD? Capacitance of unit drain area. This is drain capacitance. And CL is the load capacitance. Okay. Load capacitance ಅಂದ್ರೆ ಏನು? ಆಮೇಲೆ drain capacitance ಅಂದ್ರೆ ಏನು? Load capacitance means this is my circuit. Where is the load here? Load ಎಲ್ಲಿದೆ? ಎಲ್ಲಿರಬೇಕು load? ಎಲ್ಲಿರಬೇಕು? ಇಲ್ಲಿರಬೇಕು? ಎಲ್ಲಿರಬೇಕು? ಎಲ್ಲಿರಬೇಕು? ಎಲ್ಲಿರಬೇಕು load? RL ಎಲ್ಲಿ? ಲ್ಯಾಬ್ ಒಳಗೆ ಯೂಸ್ ಮಾಡಿದ್ದೀನಿ RL 10 kilo ohms. 10 kilo ohms or 1 kilo ohms or 100 kilo ohms something. LHC load resistance LHC output. Here in VLSI we don't use resistors, we use load as capacitors to store the charges. Okay, so ಇಲ್ಲಿ though it is not shown here, capacitor is taken as the load. That capacitance they are considering in that equation which I showed you just now. CL is the capacitance of the load capacitor. CD is the drain capacitance. Drain capacitance ಏನು ಬಂತು? Drain other we know what is drain. The parasitic capacitance which is associated with the drain. What is parasitic? Unwanted. Parasitic capacitance parasitic capacitances are the capacitances which are inbuilt. One body in blood is circuit MOSFET ಅಥವಾ wire capacitance ಇರ್ತದೆ. That we cannot remove it or that we cannot delete it. Though we don't need it, it is there. Okay. Those are the parasitic capacitors. So drain ಒಳಗೆ ಏನು capacitance ಇರ್ತದೆ, it may be required or not required, it is there. That we are taking. Okay. And RP is what? RP is the resistance of P device. P device under it is P MOSFET. Next they are taking the fault time. Okay. ಇಲ್ಲಿ RL ನೋಡಲ್ಲ, ಅದು RP ನೋಡಿದ್ರು. N ಅಂದ್ರೆ ಏನು? RL ಅಂದ್ರೆ for what? N MOSFET. P RP means P MOSFET. So fault time or RL time ಬಂತು, and this is actually rise time. Rise time or RP time ಬಂತು. Rise ಅಂದ್ರೆ ಏನು? Rise ಅಂದ್ರೆ ಏನು? 0 to 1. 0 to 1 ಸಿಗ್ನಲ್ ಹೋಗುವಾಗ ಯಾವ MOSFET ಆನ್ ಇರ್ತದೆ? P or N? 0 to 1 ಹೋಗುವಾಗ ಔಟ್ಪುಟ್ ಯಾವ MOSFET ಆನ್ ಇರ್ತದೆ? pull up on ಇರ್ತದ pull down on ಇರ್ತದ pull up on ಇರ್ತದ because output is going high, it is pulling up. Therefore we take for rise time we take RP and for fall time we take RF. Okay, so ಇದೆಲ್ಲ equation ನೋಡಿ ಸ್ವಲ್ಪ ತಲೆಗೆ ಇರ್ತದ. ಸಮರಿ ಏನಂತಂದ್ರೆ rise time for K P MOSFETs in series is K times TR. Now summary already ಹೇಳ್ಬಿಟ್ಟಿದ್ದೀನಿ. ಏನದು summary? ಇಲ್ಲೇ ಅದು summary. ನಾನು ಏನು ಹೇಳಲ್ಲ. So whenever MOSFETs are in series, okay, these two MOSFETs are in series. So here these are which MOSFETs? ಯಾವ MOSFET ಇದೆ? P MOSFET or N MOSFET? N MOSFET or P? N MOSFET. So when N MOSFETs are in series, your fall time will double. What is fall time? Output is falling. Output is falling. So it will not fall immediately. So time ತಗೋತದೆ. Yes, time ತಗೋತದೆ. It will take twice the time which it was taking for 1 NMOS. 1 NMOS is 1 second ತಗೊಳ್ಳಿಕ್ಕೆ now 2 NMOS are in series, therefore it will take 2 seconds to fall down. ಗೊತ್ತಾಯ್ತು ಯಾಕಂದ್ರೆ signal should pass to this and again it should pass to this. So signal pass ಆಗಲಿಕ್ಕೆ time ತಗೊಳ್ತದೆ. Yes, ಏನು time ತಗೊಳ್ತದೆ? T is equals to R into C. Similarly, ಇಲ್ಲಿ equivalent resistance ಏನಾಯಿತು half ಆಯಿತು. Therefore, the fall time will reduce by half. ಇಲ್ಲಿ fall time doubles. ಇಲ್ಲಿ fall time will be reduced to half. So this is series and parallel transistor effects. This is the delay characteristics of cascaded gates. Andre ಏನು when you cascade different gates, delay ಹೆಂಗೆ ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಅಂತ ನೋಡಿ. Or to take simple direct project ಮಾಡೋದ್ರಲ್ಲಿ Vlsi ಮೇಲೆ ಇಲ್ಲೊಂದು ಪ್ರಾಜೆಕ್ಟ್ ಇದೆ. ಏನು ಪ್ರಾಜೆಕ್ಟ್ ಐತಿ? whether there are 3 cases where all 3 cases are same or different. Whether all 3 cases are same or different. Same or different? Same. So expression wise same ಇರಬಹುದು, but circuit wise different ಅದ. First circuit ಒಳಗೆ ಏನದ ಹೇಳ್ರಿ? They are using 8 inputs. So 8 input NAND gate use ಮಾಡ್ಯಾರ. ನೀವು ಡಿಸೈನ್ ಮಾಡಬಹುದು 8 input NAND gate. ಎರಡನೇ ಕೇಸ್ ಒಳಗೆ ಏನು ಮಾಡ್ಯಾರ? 4 input NAND gate ಎರಡು ತಗೊಂಡಾರ. ಹೌದಾ? And third case ಒಳಗೆ ಏನು ಮಾಡ್ಯಾರ? 2 input NAND gates 4 ತಗೊಂಡು then they have brought the same expression at the end. ಇಲ್ಲಿ load ತೋರಿಸ್ತಾರೆ. This is capacity load CL. Okay, fine. ಈಗ ಇದರೊಳಗೆ ಎಕ್ಸ್ಪೆರಿಮೆಂಟ್ ಏನೈತಿ, ಪ್ರಾಜೆಕ್ಟ್ rig up all the 3 circuits in your cadence. Then you try to calculate the delay of first circuit, calculate the delay of second circuit, calculate the delay of third circuit. Though answer is correct, all 3 circuits will give you different delays. All the 3 circuits will give you different delays. Okay, and also try to calculate the power also. Power consumption. One first circuit will just power consumption, the second circuit will just act, the third circuit will just act. Then at the end you can conclude. Okay, now the functionality in ಬೇಕಂದ್ರೆ ನಾವು ಫಸ್ಟ್ ಒನ್ ಪ್ರಿಫರ್ ಮಾಡಬೇಕು and third one ಪ್ರಿಫರ್ ಮಾಡಬೇಕು. Second one will give you intermediate result. First one will be best or third one will be best. ಅದನ್ನು ನೀವು ಮಾಡ್ಕೊಳ್ಬೋದು. ಗೊತ್ತಾಯ್ತು? So here what they are discussing, other concept we will discuss madata. So it depends on circuit complexity and how we do the connections, that will cause the effect on delay and other parameters. Okay. Next is body effect. What is body effect? Body effect. ಕಲ್ತಿರಲ್ಲ ಬಾಡಿ effect ಅಂದ್ರೆ ಏನು? What is body? What is body? Fourth terminal of MOSFET. What is body effect? Body effect is nothing but when body effect is when body of the MOSFET is not shorted to the source. When body of the MOSFET is not shorted to the source. When fourth terminal is not shorted to the source of that MOSFET, it will affect the threshold voltage of that MOSFET. ಇಲ್ಲಿ you can see the example. PMOS ನೋಡ್ರಿ. PMOS check the body connection. Body ಹೇಳ್ಬೋದು, bulb ಹೇಳ್ಬೋದು ಅಥವಾ substrate ಹೇಳ್ಬೋದು, ಮೂರು ಸೇಮ್. Check the body connection. ಏನಾಗಿದೆ? Body is connected to source. ಇದೇ source, main source. Body is shorted to source. Body is shorted to source. That is shorted to VDD. That is secondary. Okay. So body is shorted. All bodies are shorted to source. ಇದು ನೋಡಿ ಕೆಳಗೆ ನೋಡಿ ಈ source ಗೆ ಬರೆದಿದ್ದೀವಿ ನಾವು. ಅಂದ್ರೆ ಕೆಳಗೆ ಏನು ಬರೆದಿದ್ದೀವಿ? Drain source, drain source, drain source, drain source. Now you see the last transistor. Zoom ಮಾಡ್ತೀನಿ. Last transistor whether source and body are shorted or not. Last transistor source and body are shorted or not. They are shorted. ನೋಡಿ ಇದು body with source ಎರಡು ಶಾರ್ಟ್ ಆಗಿದೆ. Take the next transistor. ಇದು ಈ transistor whether the body is shorted to its source or no. It is not shorted. ಕೆಲವೊಬ್ಬರಿಗೆ ಏನು ಅನಿಸ್ತೈತಿ ಇದು ಬಾಡಿ ಇದು ಸೋರ್ಸ್ ಆದರೆ ಇದು ಸೋರ್ಸ್ ಇದರ ಸೋರ್ಸ್ ಏನಿದೆ ಇಲ್ಲೇ ಐತಿ ಬಾಜು. ಸೊ ಬಾಡಿ ಅಂಡ್ ಸೋರ್ಸ್ ಆರ್ ನಾಟ್ ಶಾರ್ಟೆಡ್. ಹೌದಾಯ್ತು. ಸೊ ನ್ಯಾಂಡ್ ಗೇಟ್ಸ್ ಅಥವಾ ಡಾಟ್ ಪ್ರಾಡಕ್ಟ್ ಒಳಗೆ ಈಗ ಬರ್ತದೆ ಯಾವಾಗಲೂ ಎನ್ಮೋಸ್ ಒಳಗೆ ಬಾಡಿ ದಿಸ್ ಬಾಡಿ ಈಸ್ ನಾಟ್ ಶಾರ್ಟೆಡ್ ಟು ಇಟ್ಸ್ ಸೋರ್ಸ್. ನೋಡ್ರಿ C1, C2, C3 consider battery. C1, C2, C3 are drain capacitance. CD, it is the capacitance at the drain point. Drain source. So it is drain. E drain is the capacitance. Okay. So don't think that ಇದು short ಆಗಿದೆ ಇಲ್ಲ ಈ ಡಾಟ್ ತೋರಿಸಿಲ್ಲ ನೋಡಿ. ಇದು ಡಾಟ್ ತೋರಿಸಿಲ್ಲ. So body effect ಅಂದ್ರೆ ಏನು? ಇಲ್ಲಿ body effect ಕಾಣಿಸ್ತಿರೋದು ನಮಗೆ. Body is not shorted to the source of the same MOSFET. ಇದರ body ನೋಡಿ ಸೀದಾ ಕೆಳಗೆ ಹೋಯಿತು ಇಲ್ಲಿ shorted. ಇದರ body ಸೀದಾ ಕೆಳಗೆ ಹೋಯಿತು ಇಲ್ಲಿ shorted. ಇದರ body ಹಂಗೆ. So ಈ ಮೂರು ಟ್ರಾನ್ಸಿಸ್ಟರ್ body is not shorted to their sources. In this case, the threshold voltage of all these three transistors will vary. How it will vary? The equation ಬರ್ಕೊಂಡಿದ್ರಿ ಬಾಡಿ ಇಫೆಕ್ಟ್ ಒಳಗೆ ಹೌದು ಗೊತ್ತಾಗಿದೆ ನೋಡೋಣ ಪಾರ್ಟ್ ಬೈ ಪಾರ್ಟ್ ಕೊಟ್ಟಾಗ here ಇನ್ನೊಂದು ಕಾನ್ಸೆಪ್ಟ್ ಅದ ಏನ್ ಕಾನ್ಸೆಪ್ಟ್ ಅದ ಅಂದ್ರೆ you just see this diagram timing diagram ಈ timing diagram ಒಳಗ voltage will A B and C are ground or zero. D is 0 but here it is turning on. So D is 1. D1 ಅಂದ್ರೆ ಏನಾಗ್ತದೆ ಹೇಳಿದ್ರೆ NMOS ಅಷ್ಟೇ ಹೇಳ್ತೀವಿ PMOS ಬಿಟ್ಟಿದ್ದೀವಿ ಅಥವಾ PMOS ತಗೋರಿ ಇನ್ನು ಸಿಂಪಲ್ ಆಗ್ಬೋದು D ಅಷ್ಟೇ ಆನ್ ಮಾಡಿದ್ವಿ ಏನಾಗ್ತದೆ ಔಟ್ಪುಟ್ ಏನಾಗ್ತದೆ ಹೇಳಿ D ಆನ್ ಆಯಿತು D is 1. Okay, and A, B and C are zeros. Here ಆಗ್ತದೆ so ಇದು ಆಫ್ ಆಗ್ತದೆ A, B and C are on. So what is the output? Output is this other. Output is other 1. ಹೌದಾ ಯಾಕೆ ಬಂದದ ಹೇಳಿ this three transistors are on. When they are on, LED is shorted to output. Therefore, output is 1. Now, what we have to do? We have to do the analysis of voltage at this point. We have to do the analysis of voltage at this point, E point. That voltage we will call it as VC1. Voltage at C1. E point. So when I give D as 1, D ಏನಾಗ್ತದೆ D ಏನಾಗ್ತದೆ ಈ MOSFET ಏನಾಗ್ತದೆ D1 ಕೊಟ್ಟರೆ MOSFET ಏನಾಗ್ತದೆ ಏನಾಗ್ತದೆ I am asking only on or off. If I give D1, then MOSFET will be on or off? On. Okay. If on ಆಯ್ತಂದ್ರೆ ಇದು ಏನಿದೆ VDD ಐತಿಲ್ಲ ಔಟ್ಪುಟ್ ಯಾಕೆ VDD ಐತಿ ಇವು ಆನ್ ಅದಾವ so VDD shorted to output. This VDD will come here, this VDD will appear at this point. Correct? Therefore, ಇದು D on ಮಾಡಿದ ತಕ್ಷಣ ನಿಮ್ಮದು VC1 also has risen up. valve up ಕೊಟ್ಟಿದ್ದೀವಿ ಅಂದ್ರೆ ಏನು ಇದು ಏನು ಹೇಳಿರ್ತದೆ ಇದು ಆನ್ ಅದ VDD is coming Therefore, voltage at this point Vc1 will also rise as D rises. ಹೌದಾ? D1 ಅಂತಂದ್ರೆ then MOSFET ಆನ್ ಆಯಿತು, ಇಲ್ಲಿ VDD ಇದ್ದಿದ್ದು ಇಲ್ಲಿ ಮಟ್ಟ ಬಂತು. Therefore, ಇದು high ಆಯಿತು. That is Vc1 is rising to VDD. Next ಏನು ಮಾಡ್ತೀವಿ? D will make it 0. D will make it 0. ಏನಾಯ್ತು ಇದು? ಆಫ್ ಆಯ್ತು. ಆಫ್ ಆದ್ಮೇಲೆ ಇಲ್ಲಿ ಮತ್ತೆ ಇಲ್ಲಿ ಕನೆಕ್ಷನ್ ಹೋಯ್ತಲ್ಲ, ಓಪನ್ ಸರ್ಕ್ಯೂಟ್ ಆಯ್ತಲ್ಲ. ಓಪನ್ ಸರ್ಕ್ಯೂಟ್ ಆಯ್ತಂದ್ರೆ ಇಲ್ಲಿ ಮತ್ತೆ ಈ ಕನೆಕ್ಷನ್ ಹೋಯ್ತು. ಬಟ್ ಈ ವೋಲ್ಟೇಜ್ ಎಷ್ಟು ಬಂತು ಅಂತ ಈಗ VDD, ಯಾಕಂದ್ರೆ ಆನ್ ಆಗಿ ಆಫ್ ಆಗಿದ್ದು. ಆನ್ ಆದ ತಕ್ಷಣ VDD ಈ ಮಟ್ಟ ಬಂದಿತ್ತು, ಈಗ ಸಡನ್ಲಿ ಆಫ್ ಆಯ್ತು. ಇದು ವೋಲ್ಟೇಜ್ ಎಷ್ಟು ಅಂತ VDD. ಹೌದಾ? That VDD will actually 0 ಹೋಗ್ಬೇಕಲ್ಲ, ಬಟ್ ಹೋಗುದಿಲ್ಲ. That will slowly discharge because there is a capacitor. Capacitor cannot discharge immediately. It will take time to discharge. Therefore, in the diagram you are seeing, it is not suddenly dropping. It is taking time to drop. Okay, so इसका concept भाड़ लो. See next topic in the next class.